Imagine I give you a Markov chain with a distinguished set of golden states, like this one. This chain has good runs that visit golden states infinitely often. And here you have an example. The run now is going to alternate between states 6 and 8 forever. Their chain also has bad runs that visit golden states finitely often. And again, here you have an example where the chain gets trapped in the states 12, 13, 14 forever. Imagine I give you a restart button, a button that you can press at any time in order to restart the chain. Using this button, you can enforce a good run. How? Well, imagine, for example, that the chain starts to execute and it reaches state 7. Now you know that no extension of this run will be good, so you can restart. Now, if now the chain continues like this, goes to 1, 2, and 12, again, you can see that no extension can be a good run, so you can restart, and you can continue like this until the chain produces a good run. So, to make things more interesting, imagine now that I hide the Markov chain from you. So you only know that behind this box there is some finite state Markov chain. Now if you see this run, you cannot be sure that you should restart. You could do it before. You were restarting before because you knew that this was the Markov chain and that 7 was here. But now this could be the Markov chain and then you shouldn't have restarted. Or the Markov chain could be something like this. The Markov chain can be any finite Markov chain. The question now is, can you still enforce a good run if you don't know the Markov chain? This is the question that we are going to answer in this paper.
Hello, I'm Cas Weershoven. In my talk we will be talking about the paper Linear Time Model Checking Branching Processes by Stefan Kiefer, Pavel Smukhin and me. In this paper we will be considering the problem of qualitative model checking branching processes against LTL formula. Branching processes are a stochastic model generating infinite trees that generalizes both Markov chains and transition systems. The problem that we are considering is whether it is true with probability 1 that all the branches of a tree generated by a branching process satisfy an LTL formula, or that the probability is true that the probability is 0 that all the branches of a tree generated by a branching process satisfy an LTL formula. These problems are p-space complete for both Markov chains and transition systems, and we show a matching bound for branching processes using an automata theoretic approach.
Hello. In my talk I will talk about an interesting extension of linear temporal logic that is not that well known. It's called quantified propositional linear temporal logic, which has the full expressive power of omega regular languages and which can be used to define interesting notions in the context of formal verification whenever you're working with LTL. And in particular, the lower bounds that we prove for the model checking problem of this logic over probabilistic systems might be interesting for further hardness proofs in the area of formal verification of probabilistic systems. And one such application I will also talk about is vacuity checking, for which we then can also establish a new hardness result using our more general result for QLTL model checking.